All right, welcome everyone. Just so that everyone knows, we have an exam next class, in class. Same procedure as with the first exam. You're gonna come into the classroom. I'll give you an exam on paper. You're allowed to bring a calculator, but no other notes are gonna be allowed. The exam will be 10 questions done during the next class period. The exam covers chapters 4 and 5, which deals with general vector spaces and applications of eigenvalues. I posted last year's exam 2 to Canvas, and later today, I will post more practice problems. So the last time we reviewed chapter 4, now we're going to review chapter 5 in its entirety. So the first thing are these definitions. We've been talking about them a lot, so you probably don't need me to repeat them, but we have what's called an eigenvalue-eigenvector pair, which is a solution to the formula AX equals lambda X. The thing we like about this type of equation is that it shows what X values are being scaled instead of rotated. So they're either going to shrink or stretch, but they're not going to rotate left and right at all. The way we find the eigenvalues and eigenvectors is by solving the characteristic equation, which is the determinant of A minus lambda I, where lambda is a scalar and I is the identity matrix. Once we have solutions to A minus lambda I x equals 0, we can think about all the solutions as a subspace, because the span of all the eigenvectors will give you the solution to A minus lambda I. So the eigenspace is just the span of the eigenvector. The first theorem that you should know is the triangular theorem. A lot of times we're going to reduce matrices to their triangular form so that they are a little easier to work with. The eigenvalues of a triangular matrix are the entries on its main diagonal. So the first thing that needs to be understood is what is a triangular matrix. And a triangular matrix is a matrix where there's a triangle of zeros, like that. This can be either below or above. It'll apply the same idea. Okay. So once we have that triangle of zeros, we just list off the diagonal elements, A11, A22, A33. In this case, we're a 3x3 matrix. And that gives you a good head start. So this will be a theorem that you use a lot. You don't have to explain it as long as it actually applies. So this is related to the determinant of a triangular matrix, which is just the product of the diagonal terms. So when we subtract off lambda I, we're subtracting lambda from all these diagonal terms. And so if you want to set this equal to 0, the determinant, well, then lambda has to equal A11 or A22 or A33. This equation, the determinant of A minus lambda I, is called the characteristic equation of A. It is a polynomial that you can solve for the roots. Sometimes the roots are going to be real numbers. Sometimes they're going to be imaginary numbers. The thing that you should know for this is how to use the quadratic formula. With complex numbers. So in the past, when you've done the quadratic formula, they've said don't continue if you have a negative square root. Here, we're going to be using I. So you'll be able to take it a step further. I want you to know the quadratic formula because that is the easiest way to solve for the complex roots of a polynomial. Unless it's like really simple, like lambda squared plus 1 equals 0, it'd be difficult to find the roots. So remember that's negative b plus or minus the square root of b squared minus 4ac all over 2a. And these are what the lambdas will equal when you have a quadratic function. So that would correspond with a 2 by 2 matrix. Next, we have the diagonalization theorem, which is a theorem that allows us to take certain matrices and write them in a diagonalizable form. This occurs when you have n linearly independent eigenvectors. When you have n linearly independent eigenvectors, then you can write A as PDP inverse, where D is a diagonal matrix of the eigenvalues, and P is a matrix with the eigenvectors as columns. And an important thing is that order must match. You probably would do this automatically, but it is important that if the first entry is lambda 1, then the eigenvector corresponding to lambda 1 has to be the first column of P. If we have a diagonalizable matrix, that means we have n linearly independent eigenvectors, and that creates a basis for Rn, which we will call an eigenvector basis. So the main draw of the diagonalization theorem is that we can use this identity. For the powers of A. And this usually is pretty easy to do because D being a diagonal matrix, the powers of D are just powers of its entries. So let's take a look at an example. Let A equal 1, 1, 0, 2. Find a formula for a to the k by diagonalizing. So what we need is P, which means we need eigenvectors, and we need D, which contains eigenvalues. So let's go through this step by step. We're trying to find a formula for a to the k, so we want to find P, D, and P inverse. The eigenvalues right off the bat you can find because this is a triangular matrix. So the eigenvalues are 1 and 2. To find the eigenvector corresponding to lambda equals 1, you set up the equation a minus lambda I times x equals 0 and find a non-trivial solution. So in this case, this says that 0x1 plus x2 equals 0, which means that x2 has to equal 0. So that gives us our first eigenvector. The eigenvector corresponding to lambda equals 2 is done similarly, where we subtract 2 along the diagonal, And we get this formula here. The second line of this formula doesn't tell us anything, but the first line does. This says negative x1 plus x2 equals 0. And a solution to this is 1, 1. That's a non-trivial solution. Now, you do want to be careful. I'm saying one solution to these things, but in reality, you'd want to find the parametric vector form of the solution to a minus lambda I x equals 0, because it's possible that the eigenspace is more than one-dimensional. For most of the examples we've seen, the eigenspace is one-dimensional, and there's only been multiplicity 1. However, in other examples, you'll be able to see eigenspaces that are two-dimensional or more. Okay, so we have our eigenvalues and our eigenvectors. Therefore, we can create our P, D, and P inverse matrices. P is just V1, V2. While D is lambda 1 and lambda 2 on the diagonal. The inverse of P was found using the 2x2 inverse formula. And we get this formula for A to the K. We have P d to the K P inverse, where d to the K is the eigenvalues raised to the kth power. 1 to the K is just 1, so I left that as 1. 2 to the K, we'll leave it like that. I then started multiplying these matrices together so that I could get a final answer. And this is the solution. A to the K equals 1 to the K minus 1, 0, 2 to the K. Whenever you see a formula like this, it's probably a good idea to do a quick check. So you can check two easy examples, K equals 0 and K equals 1. K equals 0 is A to the 0, which in linear algebra means the identity matrix. Instead of 1, it's the identity matrix. And then when K equals 1, that should just be your original A matrix. So we have A to the 0. You plug in K equals 0, and you do in fact get the identity matrix. And when you plug in K equals 1, you do get our original matrix back. Easy way to double check your work. Any questions about this example? All right. The next thing that we discussed was complex eigenvalues. And in order to do that, I need to have a little bit of complex numbers under my belt. So a complex number is a number of the form z equals a plus bi, where a and b are real numbers and I is the formal symbol satisfying the relation I squared equals -1. There's a lot of different interpretations of I depending on what field of study you look at. In our class, we're using I as a sort of tool in order to help explain real matrices. And that leads to some interesting properties. There are two real parts of a complex number. The first part, A, is called the real part of Z, and the B term is called the imaginary part of B. One thing that I want you to know is that the imaginary part of Z does not have I. So this is important. the imaginary part of Z is just the part that's in front of the I, not including the I. So the real part and imaginary part of a complex number are both real numbers. And so, in some examples, we'll be using the complex number system in order to help us answer questions. We can add complex numbers and multiply complex numbers as long as we remember the rule that I squared equals -1. So, for any matrix, we can create a characteristic equation. And that characteristic equation is going to have roots. It's nice when the roots are real, but if they're not real roots, there will be complex roots. And so it can be helpful to understand how complex roots affect a real system. Here is an example of a real matrix being applied to real numbers that can be explained with complex numbers. If you think about this linear transformation, A equals 0, -1, 1, 0, you'll see that it represents a counterclockwise rotation by 90 degrees. So what I want to relate this to is linear transformations that we talked about before. So we take a point here. Well, actually, let's start with a point. Start with a point here. This is 1, 0. This goes to the point 0, 1. Remember that we talked about the columns of the standard matrix for a linear transformation give you the places where the standard bases are sent to. So 1, 0 gets sent to 0, 1, and 0, 1 gets sent to -1, 0. So you can see that this is a rotation by 90 degrees. The action of A is periodic. Since 4 quarter turns will get you back to where you originally started. And this transformation has no real eigenvalues because no real vector will be only stretched or shrunk. All vectors are being rotated. We can confirm this with the characteristic equation, which is lambda squared plus 1 equals 0. That has complex roots I and -I. Note the complex conjugates. In eigenvalues and eigenvectors. So comparing these two, and also, as we'll describe in a second, these two. This is always going to happen when you have a real matrix with complex eigenvalues. Your roots will be complex conjugates, and your eigenvectors will be complex conjugates. So what we see is that if we use, if we have the eigenvalues I and -I, we can find the eigenvectors. This slide doesn't actually show you how you would find the eigenvectors. So let me show you what that would look like. We would look at A minus I, which looks like -I negative 1, 1, negative I. So this tells you that negative I x1 minus x2 equals 0. Or this is actually easier to find a solution using the second line, x1 minus I x2 equals 0. So that means that x1 equals I x2, which corresponds to 1 I. We did talk about complex conjugates in reference to rationalizing denominators. In this case, it's not completely necessary. You could rationalize the denominator to solve for x1 in terms of x2. But that's going to be all you need for this part. Because once you have one of the complex eigenvalues, you know its conjugate is also going to be a complex eigenvalue. So we have 1 minus I and 1 I as the eigenvalues. It's kind of interesting. What happens is that in the real world, no vectors get stretched. But in the complex world, there are some vectors that get stretched, but they get stretched by a complex factor, which kind of ruins the intuition of what stretching means. But it follows from the definition. This is just a lambda. So it's not too far off from what we've been doing already. Question here.
I'm just curious. So why is it that for x1 it's 1? Like typically what I've been finding is like when you go through the homework or stuff, typically when it's 1, it's usually referencing the free variable or like whatever equals to itself. So I'm just kind of curious, wouldn't it be I for x1, since you would just use the fact that x2 can be equivalent to 1, x1 can come out as I?
Yeah, you could do that. What I did here is I took this second equation right here that comes from the second line, but you can use either equation. I liked this second equation because it's easy for me to plug in 1 into x1 to get a solution for x2. While if I plug in negative I x1 minus x2 equals 0, it might be harder for me to find what x2 needs to be. So for example, if I have x1 equals I, then I have negative I times I minus x squared equals 0. That's a negative 1 minus x squared equals 0. So that means that 1 minus x squared equals 0. So x2 equals 1. So that means you could also use I1. Wait, did I do that right?
From what I'm seeing, you did it correctly. Yeah.
Okay, yeah, I was just a little confused for a second. Anyways, so you can use either equation you like for the eigen vector, because you can just multiply it by any constant and it's still an eigenvector as long as that is not 0. So you can say that v1 equals 1i, or v1 can equal I times 1i. Or you could even say v1 equals negative I times 1i. Whatever works, whatever form you get to first, that's fine. You don't need to make the first element 1 or any other element 1. Any other questions about this complex eigenvalue example? All right, then we're gonna do some participation. So let me get the iClicker up and running. Here we go. Sorry, it's not responding. My app. Okay. Okay, just got it up and running. So the first participation question, consider the matrix 2, 2, 2, negative 1. First thing I want you to do is find the eigenvalues. And I have 4 options here. So go ahead, I'll give a minute or two for you to do that. All right, I'll keep it open for now, but I'll go over the solution. So what you need to do in order to find eigenvalues is to set up the characteristic equation. That's going to be the determinant of 2 minus lambda to 2 negative 1 minus lambda, which is 2 minus lambda times negative 1 minus lambda minus 2 times 2. I'll distribute everything out. Negative 2 lambda, positive lambda squared minus 4, which gives us lambda squared minus lambda minus 6, which is lambda minus 3 times lambda minus plus 2. So the solution is lambda equals negative 2 and 3. Any questions about how I found the eigenvalues here? All right. Next question. Using the same matrix, find the eigenvectors. So I'll give a little bit of time for that, and then I'll show you how I would approach this problem. All right. So, in order to find the eigenvectors, you need to find the solutions to a minus lambda I x equals 0. A minus lambda I x equals 0. So let's start off by subtracting off the diagonal elements. So for lambda equals -2, we have 0, 2, not 0. 4, 2, 2, 1, x equals 0, which means 4x1 plus 2x2 equals 0, or x1 equals -1/2 x2. Alternatively, you could just write this as in any way that you want to, just as you know that you have to plug in values that look like -1, 2. Right, so that's one solution. For lambda equals 3, we get -1, 2, 2, -4, which once again means -x1 plus 2x2 equals 0. So x1 equals 2x2, which corresponds to 2, 1. And that is answer choice B. With these types of questions, I give specific examples of eigenvectors, but on the exam, you can use any non-zero scalar multiple of the eigenvectors, as long as it sort of makes sense for the problem. Any questions about this example? All right. Then let's move on. I wrote out the solutions here, if you would like to take a look at them. And the next thing that I want to discuss are the applications to eigenvectors. First one we talk about will be Markov chains, which have to deal with probabilities of moving from one state to another state. So we gave an example with the refrigerators, not refrigerators, the TVs, where they could be fully functional and then require maintenance and then beyond repair. We also talked about the population example, where people are moving between city and suburbs. And we also discussed other examples that use similar ideas, but are not necessarily Markov chains, like the predator-prey model. So a Markov chain uses probability vectors, which are vectors that just add up to 1. It's just a column vector where the entries add up to 1. Sometimes you'll see this written as a row vector. Doesn't really matter, the same idea applies. A stochastic matrix is a matrix that describes probabilities, and so it has probability vectors. If you read down each of the columns, you'll see that they add up to 1. And another thing to note is that these, because they're probabilities, they are non-negative. A Markov chain is a sequence of probability vectors, x0, x1, on and on, together with a stochastic matrix P, such that in order to get to the next observation, you just multiply the previous observation by P. This gives us the cumulative formula, xk equals p to the k times x0. So you'll always be able to represent any point in time by a matrix power times the initial condition. This is why we require that the conditions do not change over time. We are always using the same Markov matrix. So let's discuss an example. Let A equal 0.95, 0.05, 0.03, 0.97. Analyze the long-term behavior of the dynamical system defined by x sub k plus 1 equals A times x sub k with initial condition 0.6, 0.4. So what this could represent is a population matrix. But in this case, we have 60% of people are in the city, while 40% of people are in the suburbs. And so that allows us to express it as a probability vector. Finding the long-term behavior means we want to know what happens to x as k approaches infinity. And because of the rules we set up, we know that x to the k equals a raised to the k x0. So we want to find the long-term behavior of a raised to the k. Well, a raised to the k, you can do two things here. You can create a matrix like this and find what it is, find what the solution is. However, we know that the steady state solution corresponds to the eigenvector corresponding to lambda equals 1. This was a theorem that we gave, and it might be a little bit unnerving to just skip to this step. So using the diagonalization matrix will be fine. You'll see the same sort of idea where the eigenvalue corresponding to lambda equals, the eigenvector corresponding to lambda equals 1 is the only thing that's sort of remaining in the equation. Alternatively, you could express x0 as a coordinate vector. Where B is an eigenbasis. This is the technique that we talked about at first, and this corresponds to writing out x0 equals C1, V1, lambda to the K, sorry, C2, V2, lambda 2 raised to the K. What I want to emphasize is that these two ideas are exactly the same idea. In both cases, you need to know what the eigenvalues and the eigenvectors are. However, the second example is a little bit easier because it makes it a little bit more clear that the only thing that matters is the eigenvector corresponding to lambda equals 1. Let me show a solution from first principles using eigenvalues and eigenvectors. We create the characteristic equation and we get two eigenvalues, lambda equals 0.92 and lambda equals 1. So our solution, we know, is going to be based off the eigenvector corresponding to lambda equals 1. but we won't skip ahead yet. We find eigenvectors for each of the eigenvalues, which will be 1, -1, and 3, 5. Which allows us to express our matrix A as this diagonal formula. The neat thing is that as k goes to infinity, d to the k is only going to have one element, which is 1. That's why the eigenvalue corresponding to 1 is the most important. The other eigenvalues are going to be less than 1, and so when you raise them to the kth power, they will go to 0. 0.92 raised to the k approaches 0. Then what's done is the entire matrix multiplication to see what the solution looks like as time goes on. And what we get is this is A raised to the k. No matter what x0 is, x to the k is 0.375, 0.625. If you look at this matrix multiplication, in the original lecture that I had for this problem, I wrote this down incorrectly, but I figured it out now. If you do the matrix vector product here, you'll have these values, 0.375, 0.375, times something that adds up to 1. So no matter what, this always equals 0.375 here. And similarly, for the second row, both of these are 0.625, and they are multiplied by something that adds up to 1. So you'll always have 0.625 as the solution. The other technique would be to express x0 as C1 V1 plus C2 V2. Then A to the k x0 equals C1 lambda 1 to the k V1 plus C2 lambda 2 raised to the k V2. Or, because we already have values here, we have C1 times 0.92 raised to the k times 1 - 1 plus C2 times 1 raised to the k times 3, 5. And you can see that as k goes to infinity, this term will go to 0. The only thing that's left over is our V2 term. All right. So what I could ask you to do after you have solved one of these problems is to draw out the trajectory. In this example here, I don't have a trajectory for this example, but I could create one if I was interested. So let's create. Actually, I'll just draw it here. The main point is that all these points live in this area, and no matter what, every initial condition is going to go towards this point. And so we would say that this point X is an attractor, 0.375, comma 0.625. Question back there?
So if we were to be asked like to draw the graph or whatever, what would be like, I know that like the examples that are given are kind of like elaborate, the graphs.
Right.
What would be like an acceptable answer? Like, do we have to go that in depth, or we just, if you just want to like get to the point that it's going for a certain point?
Yeah, there's gonna be two main points about graphs that I will discuss when we get to a graph problem. But yeah, there are a couple of things to look out for. I think I will describe it in this example. This example asks us to plot several trajectories of the dynamical system. X sub k plus 1 equals a x sub k, where a equals 0.800.64. So right off the bat, you can say what the eigenvalues are. They are 0.8 and 0.64. So we can write out this solution using the coordinates C1 and C2. Remember that these coordinates are what constants you need with the eigenvectors in order to create your initial condition. From this, it's clear that as k goes to infinity, both of these terms go to 0. And so both the x and the y component, or the x1 and x2 component, will approach 0. There are two main things that I want you to point out. I want you to note the direction of arrows. And two, I want you to note which eigenvectors are dominant. So let me explain what that means. In the case that we had eigenvalues of 0.8 and 0.64. Both of these have an absolute value that's less than 1. And because our solutions have x to the k, that means that when lambda is less than 1, we're going to have exponential decay. Thus, all of these arrows are pointing towards the origin. On an exam, I will ask you to put down arrows showing the direction. The next thing that I want you to do is to use the eigenvalues to determine which direction things go. So you can imagine that if you have a point here and you know it's going towards the origin, you could say it goes like this, right? Or like this. But we see that most of the solutions are more like that first example. The reason for this is because the dominant part of x sub k is corresponding to lambda 1. What I mean by this is that this will decay slower than the 0.64. The 0.64 raised to the k will go to 0 quicker, and so it won't be as important. That is why most of these vectors look like they're pointing towards 1, 0, as opposed to pointing towards 0, 1. The only arrows that stay by 0, 1 are all the vectors that are along that eigenspace of the span of 0, 1. And that corresponds to having a C1 term of 0. So if you're familiar with which functions dominate other functions, you'll be able to figure out which direction or which eigenvalues the solution should go. So, for example, this is the span of V1, this line here, which you could just also call the x-axis. While this line here is the span of V2. Okay. If you zoomed out even further, what you would see is that most of the vectors look like they're pointing towards the x-axis. Right. Question back.
To get like, let's say they get like, we basically just need like, if you need like, if you just graded, it's gonna be like, as long as we have like most of the vector towards wherever the dominant part is, and then
Mhm.
say it's a tractor or whatever we're going to, as long as we get that idea, then we'll be fine.
Right.
Okay.
Yes. You would lose some points if you said that the trajectory of this vector is like this. You would lose some points doing that. Because it's more correct to say the trajectory is like this. But I'm not going to be scaling based off of artistic ability. Exactly. Yeah, because it is nice in this example. We can't think about it as the x and y axis, but that is only because the eigenvectors are 1, 0, and 0, 1. So here, this shows that y goes to 0 faster than x, which is why we get that effect. The y value corresponds to this vector here, and the x value corresponds to the first part. So that's one example of trajectories. Question here?
It's gonna be a really stupid question. How did we get the vectors to be 1, 0? Like, are we gonna have to like, is that given, or is that just something we're able to tell from the standard matrix?
This is based off, they are eigenvectors of the matrix A. So if you have a problem where you have to plot trajectories, the eigenvectors are going to act as sort of barriers in your problem. What I mean by that is that in this case, what you should also notice is that everything in quadrant 1 stays in quadrant 1, and the same for all the other quadrants. So these eigenvectors, or their span, separates the Cartesian plane into 4 separate regions that all approach 0. So the reason why there's a 1, 0, and 0, 1 are the important vectors here is because they are the eigenvectors of our matrix A. Any other questions about this example? Then let's look at another example of a repeller. So the previous example, you would say that 0 is an attractor because the solutions are going towards them. In this case, we have that 0 is a repeller because our solutions are going to be pushed away. Notice here that for our next example, we have a triangular matrix. In fact, we have a diagonal matrix. And so our eigenvalues are going to be 1.44 and 1.2. So if we have an initial condition, we can write it out using the coordinates with the eigenbasis. And what you can say here is that the first term is going to be the dominant term, because it is the one that is going to grow faster. So if you want to be very meticulous about these things, in order to determine which function is dominant or why there is function dominance, what you can do is factor out the lowest term. So by that, I mean factor out a 1.2 raised to the k. This will be times a C1 times 1.44 over 1.2 raised to the k, V1 plus C2 V2. And if you look at this product, we see that this term will have x will be greater than 1. Well, this term is equal, has an exponential base of 1. And so it's not going to grow as fast as the first term. Therefore, we get a graph that looks like this. So once again, our x sub k is related to v to the k, lambda to the k. And so, sorry, not v to the k. It's related to v times lambda raised to the k. When lambda is greater than 1, that means we have exponential growth. So that means that the arrows are pointing away from the origin. The most dominant part is due to the eigenvalue of 1.44, which is why most vectors are pointing in the same direction as v1. That is going to become the dominant term. So any vector that's not in the span of v2 will eventually look like x1, at least scaled out. So in this case, it would be wrong to say that this point here has a trajectory like that. That would be wrong. The trajectory follows v1, because that's associated to the highest value eigenvalue. We also talked about the case where you have a saddle point, where you have one part that is approaching 0 and another part that is going away from 0. It's the same idea. The lambda with the highest value is going to be the thing that's most important, most dominant, and that will be the path that most vectors take. We then discuss complex eigenvalues. So with complex eigenvalues, we lose this sort of boundedness that we had with real eigenvalues. Now, if you start in quadrant 1, you'll be going through all the quadrants in a spiraling fashion. So complex eigenvalues have spirals, and they will also demonstrate either exponential growth or exponential decay. What matters is the magnitude of lambda, which we describe like this. This is equal to a squared plus b squared. If this is greater than 1, we have growth. If this is less than 1, we have decay. So in this case, our eigenvalues are 0.9 plus or minus 0.2 I. The magnitude of that eigenvalue is less than 1, which means that we're going to have a spiral towards the origin. Because we have complex numbers, our paths will be spirals corresponding to the sine and cosine form of the exponential function. So for this type of problem, if I ask you for trajectories of a complex function, I would want you to have one spirals. And then you have to decide between growth or decay. Question here.
So would growth be like basically the same as that, but what would like a growth look like? Would it just be with the arrow pointing outwards instead, basically?
Yeah, so you can kind of start from here and move backwards. It'll look something like that, and just keep on going, and going.
Okay, so it's like the same shape, it's just that. Okay, that makes sense.
Right. The important thing is that it will eventually get away
Yeah.
from the origin. But that's not the case here because our magnitude is less than 1. So here are some trajectories. And remember, this is particularly for the case of xk equals ax k minus 1. Because these rules are different for the next topic I'm going to cover, differential equations. This sort of boundary point for the lambdas is different. So a linear differential equation will look like a system, a linear system, except the left-hand side will be equal to a derivative. However, our solution can be found by using the same methods that we talked about, finding eigenvalues and eigenvectors. The difference here is that instead of having lambda raised to the k, we have e raised to the lambda. So e raised to the lambda really determines whether there's going to be growth or decay. If lambda is greater than 0, you have growth. If lambda is less than 0, you have decay. And so this sort of barrier is now lambda equals 0 for these types of problems. So if you have a system, you know its eigenvalues and its eigenvectors. Those values are all real. Your solution will be this equation. The sum of ci vi e to lambda I t. So let's go through an example. Find all solutions of x prime equals ax, where a equals negative 1.5, 0.5, 1, negative 1, and our initial condition is 5, 4. So we need to find the eigenvalues and eigenvectors. The solution is a little bit of a different form, but still uses eigenvalues and vectors. Without giving detail, the eigenvalues are lambda equals negative 0.5 and lambda 2 equals negative 2. Both of these are less than 0. So we know based off this, we're going to have exponential decay. We then find the eigenvalues, eigenvectors corresponding to those eigenvalues, which are given in detail below. So we have everything that we need to find the solution. We know that x of t is going to equal the sum of ci vi e to the lambda I t. We know what lambda i's are. We know what the vectors are. We just need to find what the initial condition is, or for those ci's. Two equations here. We set up a system or whatever technique you want to use in order to find what the coordinate vector of x is in terms of the eigenbasis. You should get 3, negative 2. And our solution is therefore x equals 3 v1 e to negative lambda 1t minus 2 v2 e to negative lambda 2. Sorry, e to the lambda 2t. Our eigenvalues are negative, so that's why the exponent is negative. You can leave it in that form, or you can combine the vectors into one vector, like what is at the bottom. That is just done by multiplying everything out and adding. So that's differential equations when you have real solutions or real eigenvalues. We can still find a solution if we have complex eigenvalues, but it gets a little bit more complicated. Our solutions are based off of VE to lambda t. However, this is going to have a real part and an imaginary part. Typically, if your problem is given in terms of real numbers, your solution to that system should be a real function. So we create two real functions based off of x1, the real part of x1 and the imaginary part of x1. And recall, neither of these have an I in them, so they're both real solutions. So this gets a little bit complicated because we know that the complex exponential has a real and an imaginary part. So there'll be a lot of real parts, imaginary parts, and you have to separate them all out. We use the fact that e to the a plus bi equals e to the a times cosine b plus I sine of b, which we discussed as Euler's formula. So we have to use Euler's formula because we have e raised to a complex number, or you can skip all the complex calculations and just jump to these solutions here. You just have to be very careful that you read every part of this correctly. So you have e raised to the at, that's fine. The real part of v, a real function, cosine of bt, the imaginary part of v, which once again is a real function, times sine of b. And this is how you get real solutions to real differential systems of differential equations when there are complex eigenvalues. So let's go through a complex eigenvalue example. Let A equal -2, -2.5, 10, -2, and let the initial condition be 3, 3. Our characteristic equation is lambda squared plus 4 lambda plus 29. And just for fun, I'll write it like this. Lambda squared equals, lambda squared plus a squared lambda plus a squared plus b squared lambda. And it just turns out that if you have something of this form, you can write it out as a complex roots, a plus or minus bi. All right. So our solution is -2 plus or minus 5i. I would just use the quadratic formula. Don't even worry about this stuff. All right. We have complex eigenvalues. When we have complex eigenvalues, we only have to worry about one solution because the other solution is just going to be the complex conjugate. So let's find the eigenvector corresponding to -2 plus 5i. We subtract that from the diagonals of our matrix A, and we solve. Both equations can be used to solve this solution. If you use the top line, you have to do some simplifications, but you get I over 2. If you use the second line, 10x1 minus 5i x2 equals 0, well, you just have 10x1 equals 5i x2, so x1 equals 1/2 I x2. Which corresponds to V equals I2. And then the other eigenvalue and eigenvector will be the complex conjugates, where you take the negative part of the imaginary component. Thus, we know that our solution is going to be some combination of v1 e to the lambda 1 t and v2 e to the lambda 2 t. If you just look at v1 and apply Euler's formula, you will get a complex function. This is complex. You can see that there are i's in the solution. However, if you take the real and imaginary parts and then combine them in a clever way, you will turn this complex function into a completely real function. So we take the real part of x1, and that is one solution. We take the imaginary part of x1, that is another solution. And our final solution is those two components added together. We then want to find the C that gives us our initial condition, which is 1.5 and 3. So we get a solution that looks like this at the bottom. Couple things to note. Here we have lambda equals -2 plus or minus 5i. The real part of lambda was less than 0, so we're going to have a decay spiral. This is different than what we talked about with difference equations. In that case, you needed the magnitude of your lambda to be greater than 1. But here we're working with e raised to the lambda, which corresponds to e to the a, the real part of lambda. The other part of lambda, the imaginary part, is not going to contribute to exponential decay or growth. It only contributes to the spiraling part. The real part is what contributes to the decay or the growth. So we should expect to see a decay spiral from this system, which is exactly what this graph shows. If I was asking you to plot this system, I would want you, one, to show a spiral because of complex lambda, and 2, it is decay. Slash, you could call this an attractor because it's pulling things towards 0. If you think about this final equation for x of t that we have, as t goes to infinity, e to the -2t will go to 0, and so both of these terms will go to 0, or X and or Y component. All right, any questions about what I've covered in the review today? Question back there. Yeah, I'll post that when I get home tonight. Yep, I'll send out an announcement for that. Any other questions? Yes. Is there is? Yeah. Yeah, I put up a homework assignment late last week, so there is one that's up there. I think it's just 10 review questions. All right, well, that's all the time that I have for today. I will see everyone for the exam on Thursday.